Hey kiddos, this is Miss P. I'm really sorry I can't be there today, but you guys get to start biochemistry today. So, if you would please go to Schoology. You're going to want to go to this biochemistry folder, and you're going to want to click on lecture. I'm going to spend a few minutes in this video going through this organic chemistry PowerPoint. So you are going to want to download either the document or the PDF for the inorganic chemistry lecture notes. So grab one of these right now, please. Have Ms. Dubé pause it. Once you guys get these downloaded, you can go ahead and start again. All right. So you have downloaded one of these. I'm going to start this. So today we are going to just very briefly talk about inorganic molecules. So if you remember from chemistry class, inorganic molecules are things that are not living. So we actually don't use them very often in a biology class or talk about them very often in a biology class because biology is the study of life. But everything is built off of inorganic compounds. So it is really important to talk about. So the first thing that you need to remember, jog your memory from chemistry, is the term elements. So elements are pure substances, right? And they're the basic building blocks of all matter. So we have a periodic table here. You know that all of those are elements. All right, so just some examples. You have about 4 main elements in your body, and you have 16 other elements that are called trace elements in your body. And that just means you need a super small amount of them to have your body work properly. If you add in another 2 elements, you have about 98% of an organism. So 6 main elements make up 98%. Trace elements only make up about 2% of your body. Some of the elements in your body, the main one is carbon. You also have phosphorus. You also have hydrogen. You also have nitrogen. You have oxygen, sulfur, and some other ones that we don't really talk about because they're enough, small enough, trace enough that aren't huge parts of biology. So anyway, elements are made up of atoms. I hope you remember that. So here I have an atom drawn. You can see protons and neutrons inside the nucleus, and you can see electrons spinning around the outside. You know that an atom, at this point, as far as we know, is the smallest unit involved in a reaction. And it's made up of 3 smaller particles, the electrons, the neutrons, and the protons, which I think you know. All right, let me move that back over. So we know that it has a shell and that we have electrons around in the shell, and that atoms aren't happy until their shells are filled. So then they do is make bonds, right? We're going to talk about bonds in just a second. But when we're looking at an atom on the periodic table, we know that we either have the atomic number and we have the mass number. So the atomic number is the number of protons, which also means that it's the number of electrons, right? Because protons are positive, electrons are negative, so they need to equal each other. And then mass number is essentially the weight of the nucleus because electrons are so small that they don't really factor into the mass at all. So the mass number is the protons plus the neutrons. Hopefully you remember that. So we get to this concept of isotopes. We use isotopes a lot in biology to date how old something is. So it's called radioactive dating or carbon dating. And so we use these isotopes. So for an example, carbon-12 in your body is particularly stable, but carbon-14 isn't, and so it will break down. And the length of time that it takes carbon to break down, we can date a fossil using. We can also use it in medical research and a few other key components within the biology concept. So know that isotopes vary with the different number of neutrons. So if I was talking about carbon-12 versus carbon-14, clearly carbon-14 has 2 more neutrons. It can't have any more protons because then that would change the element number from carbon to like nitrogen or carbon to oxygen, whatever it was. So it's really important that you know that it's just the number of neutrons that change. So here's a really great example. Again, talking about carbon 12, 13, and 14. So every carbon atom has 6 protons, therefore has 6 electrons because it has to be neutral. But we take the protons plus the neutrons to get this mass number. So 6 plus 7 is 13, and 6 plus 8 is 14. So that kind of just visually shows you what I was just talking about. So when elements bond together, we get this thing called compounds. Compounds have 2 or more different elements joined by some sort of chemical bond. Remember, I was going to talk to you about chemical bonds. It's coming up. So a really good example of a compound is water, H2O. We're going to use water in a few days to do a water lab. We're also going to use table salt, NaCl, within that lab. So how do they join together? Well, they use bonds. And there are 2 different main types of bonds. Ionic bonds, which means I give my electron away, or covalent bonds, meaning we share the electron between us. So here's a showing of an ionic bond. So you can see sodium has 1 extra electron on the outer ring. And you can also see that chlorine is missing 1 electron on the outer ring. So if you remember from chem, ionic bonds have a metal bonded to a nonmetal. So this electron transfers to chlorine. Now that makes a bond between them, but we physically transferred the electron from sodium to chlorine. And that was the chemical reaction that then bonds sodium and chloride together to make sodium chloride. So here's just another show of this electron giving it away and therefore making a bond. Now covalent bonds are different because they physically share the electrons. So here's how we make water. Here are 2 hydrogen atoms. Here's the oxygen atom. You can see on the outside oxygen only has 6 electrons and it really wants 8. So magically hydrogen has 1 and this hydrogen has 1. But these hydrogens really want 2 in their shells. So if they come and saddle up right next to an oxygen, they can actually end up sharing one of the oxygen ones, and they then share their hydrogen one. And so you end up getting this bond using 2 electrons, 1 from the oxygen and 1 from the hydrogen. Oxygen now has 8 electrons around the outside, it's happy. Hydrogen now has 2 electrons around its side, it's happy. So we can talk about covalent bonds, and we can talk about if they're not single bonds, they can be double bonds or they can be triple bonds. And the more bonds you have, the harder it is to break. They're very, very strong bonds. So right here you can see that these 2, so right here would be a bond and right here would be a bond. So this would be a double bond. Here you can see this is carbon dioxide, and so you can see both carbon molecules double bonded to the oxygen molecules. Here, if I move this over, you can actually see that nitrogen is triple bonded with the other nitrogen. So that means it shares 3 pairs or 6 electrons total between them. All right. So just a memory jog from chemistry, acidic and basic solutions. We're going to be talking a little bit about acidic and basic solutions in biology. So the first thing that you need to know is when water breaks apart, the formal word of that is called dissociation, or so it disassociates, and it breaks into OH and H. So this is called a hydroxide group, and hydrogen is called just a hydrogen or H plus or hydronium ion group, whatever you want to call it. So if you're acidic, that means that they are releasing H plus ions. Some examples, tomatoes, the bile in your stomach, vinegar. Clearly if we use like hydrochloric acid in class or citric acid, those are in fact acids, right? Basic solutions are different. They give off OH particles. So acidic, H plus, basic, OH. And they are usually better and have a really slippery feel in water. So soap is a really good example of that. So here we have our pH scale. We start at 0 and we go to 14. That means the middle one is 7, that's neutral. So from 0 to 7 we have acidic. From 7 to 14 we have basic. The ones on the further out of the scales, like the 1s and the 2s, or the 13s and the 14s, are the more acidic or more basic. So you can kind of see some basic household items that you may have in your home that you could kind of put in different locations. What we really use pH for in biology are things called buffers. And buffers essentially fight pH change. And how they do that is by either releasing extra chemicals or taking up the extra chemicals so that they leave your body in balance. The best example of a buffer in your body is your blood. It likes to be at like 7.2 to 7.4 pH. Pretty neutral, but a little bit on the basic side. And if it gets too high or if it gets too low, it either increases the production of certain chemicals or it takes up the production of certain chemicals. So that's really, really important. So that, ladies and gentlemen, is all I have. Ms. Dubé is now going to pass out your reading notes, and you're going to spend the rest of the time doing that. If you have questions, I'll be back tomorrow, so you can certainly ask me at that time. Thanks so much. Have a good day.